So yeah, uh, yeah. So for the course, this is kind of a brief overview of the topic that will be covered. So broadly, we cover some statistical approaches to NLP, as well as deep learning based approaches to NLP, covering different problems in the NLP domain. Yeah. So yeah, to start with, these are some of the topics like the how to represent documents, how to represent words using statistical approaches like words approaches, and also looking at different n-gram models. And also you'll be taught about how to represent all these words and documents based upon some representations, distributed representations obtained using training some neural network. And so some of the major problems in NLP are all sequence labeling problems. I hope in the machine learning course you may have learned about what is a sequence labeling problem. So all these problems are, most of the problems are sequence labeling problems in NLP, and we look at those problems and again look at the statistical models which have been used to solve the sequence labeling problem, and deep learning based models which are used for sequence labeling problem. So then, no, uh, uh, so sequence labeling problems such as part of speech tagging, etc., can be seen as some lower level problems in NLP, and then understanding more about a semantics about these languages and documents requires understanding something like parsing, pragmatics, co-reference resolution, discourse, etc. And we will be looking at those kind of approaches in NLP also. Today, I will start with a sequence labeling approach to NLP and sequence labeling problems in NLP, and how these models, some machine learning models which have been used, which has been quite popular, can be used for solving such kind of sequence labeling problems in NLP.
Sir, can you close this one window? Like there is a one AB. I think it's blocking the screen.
Sorry.
There is one dialogue is coming and blocking the screen with the AB as a box. There. Is this for me or everyone else?
Okay, I think when we go to here, this one, what you find on bottom right, is it?
Yes, that is blocking the bottom right is blocking the screen.
Okay,
Yeah,
now
that
it's
one.
fine.
Yes. Yeah, now it's fine. Thank you.
Yeah. So now several problems in NLP requires us to understand the structure of the sentence, how the sentence is arranged, which is known as the syntax of the sentence. And understanding that structure mainly involves understanding what is the subject of the sentence, what is the object of the sentence, what is the verb of the sentence, and in order to understand that, you need to do something called part of speech tagging, where you need to tag any word in the sentence with its corresponding part of speech tag, part of speech. So if you go back to your high school grammar, you may have learned, okay, no different words are associated with some part of speech, like noun, what are the other part of speech?
Noun, verb, adjective, pronoun.
Adjective, pronoun, then
Um,
Or
Adverb, preposition.
adverb,
preposition, conjunction, interjection.
Adverb, position. Anything else that you still remember?
Yeah, preposition, conjunction, and interjection.
So we look at some of those different part of speech and how you can use these part of speech. Sorry, interjection, conjunction. Okay, sure. Yeah.
Preposition.
Yeah. So no. So this is basically what is meant by part of speech tag. Okay. So here you are given some sentence. Yeah. So here you are given some sentence, and you need to tag each of these words in the sentence with its corresponding part of speech. Uh, what is in? What could be in? What part of speech would you use for in?
It's a preposition.
Proposition. Proposition.
I think generally in is a proposition, right? Yeah.
Yes, sir.
But I
Prepositions.
think here one is considering, yeah,
Prepositions, right?
in is a proposition, right? Yes. In March,
It's
So
a
now
noun.
noun.
March. What would be March?
Proper
Noun.
noun.
Yeah, it's a noun and it's a proper noun, right? And yeah, sure. And if you look at New York Times, that's also a proper noun. The is
Mhm.
a determiner. Accured is a verb. So there are these different words which is assigned different part of speech tags. And this will help you to understand, okay, in a given sentence, what word is the verb, okay, and what words are the subject and what words from the object. Those kind of understanding, structure of the sentence can be obtained by doing this part of speech tagging. And that is important or that is useful for several in NLP. For instance, question answering, you want to find out the answer to some particular question. And that answer would mostly some kind of a proper noun most of the times. And if you can identify some, okay, if you find some sentence which is close enough to this question, and what would be the answer? It could be some proper noun, and you can identify the proper noun by doing part of speech tagging. In information extraction, word sense disambiguity in a word can have multiple meanings, and now if you know the underlying part of speech of the word, or can infer the right meaning of the, it will be helpful to infer the right meaning of the word. Maybe something like fly. The fly can be a house fly or something in the form of, can appear as a noun, or it can be he flies or fly. No, this bird flies. So the fly can appear as a verb also. So if you just look at fly, it may have multiple meanings. It can be, it can have a meaning corresponding to its noun part of speech. It can have a meaning corresponding to verb part of speech. So if you can also identify the part of speech of this word, then you can disambiguate different meanings of the word fly, and it can help in word sense disambiguation. And this is known as word sense disambiguation. So this is one problem, which is one of the popular problem in NLP, sequence labeling problem in NLP. We will see why it is called sequence labeling and not simply a classification. Another problem would be something like named entity recognition. Okay. So in named entity recognition, again, you want to identify what are the different proper nouns which is present in a given sentence. Again, it will be helpful for question answering, information extraction, etc. And in yeah, in so generally, all these different proper nouns also can be classified into different types. This proper noun can be, something represents temporal nature. It can be name of a person, can be name of an organization, etc. So you need to also identify what are the different types of sentence. And again, you can see that this named entity recognition also can be seen as a problem, a sequence labeling problem. And the main idea behind sequence labeling problem is that you determine the label of a particular word, not just based on that word alone, but also taking next the previous words or the surrounding words. Okay, so in order to solve these tasks, let's say part of speech tagging, one can simply think of, determining the part of speech of a particular word just based upon that word, right? So here, if you look at new, okay, if you just try to figure out the part of speech of a word like new, okay, maybe in English, you see, if it is a proper noun, people often use capital letters, right? So if there is, on the basis of that, you can say, okay, it is a proper noun. But not the case. It may not be the case for all the languages. Maybe if you look at how do you write New Delhi in Hindi? Is it written as New Delhi or something else?
Yes.
Sorry.
Yeah. No, so this is like a proper noun, right?
Yeah. I don't know if people say it is no. Or something or just New Delhi. Hello, am I audible?
Yes, sir.
Sir, is it only me who thinks your voice is breaking, sir?
The voice is breaking. Is it?
Yes, sir, your voice is breaking.
Is it fine now? Okay.
Yeah, this
Bit
time it is.
better now. Yeah, bit better now, sir. Yeah.
Okay, fine.
So can you please repeat the question that you have asked?
So what is New Delhi called in Hindi? Like when you write Hindi sentence, do you write it as New Delhi only, or you write it in something like Naya Delhi or something?
Nai Delhi. Nai Delhi.
Nai Delhi, is it? Okay.
Yeah.
So if you look at this Nai Delhi, uh, see the Nai Delhi basically together represents a proper noun, right?
True.
But then the word Nai could appear with several different contexts. Like
True.
it can be used as a noun also, not just as a proper noun. So just word based upon this word "nay," you may not be able to disambiguate if it is part of a proper noun or if it is used as a noun. So in
Correct.
English, this problem is not there because in English, if it is a proper noun, you write it in capital letters, right? You in capital letters, so you can disambiguate on the basis of that. But in several other languages, that may not be possible. And another example is what I told about this word fly. Now, fly can be a verb or can be a noun, and it is difficult to disambiguate this actual part of speech of this word just based upon the word alone. So you need to look at the neighboring context. Okay? You have to look at the previous words, the words which has appeared before this word, as well as maybe the surrounding, the neighboring context of this word, to clearly understand the part of speech tag of a particular word, right? So these sequence labeling approaches take into account not only the current word, but also what are the previous labels that has been assigned. Okay, and if the previous labels follow some particular order, what could be the current label associated with that word? It takes into account these, the context also in which this word is in order to predict the label of a word. And that is how it is different from symbol classification. Okay. So we look into this in more detail, but this is the basic context of what we are going to look at in today's class. Yeah, so some of the models, you may have studied
Sir,
already in a
can you,
machine learning course, like hidden Markov
sorry,
model.
sir. Can you remove that window, that Teams window? It is again blocking the left bottom part of the screen.
Have you heard of hidden Markov model? Hello?
Sir, it is still visible. We can still see that's half of the window.
You can still see half of the window. I
Oh,
think
now
I removed it.
now it's gone, sir.
Sure. Yeah. So you know this hidden Markov model?
Not much.
No, sir.
So we
We
covered that in the machine learning course, right? Did we cover that in the machine learning course?
mm,
Sir, we studied Markov chain and foundation of data science, but I think hidden Markov chain was not covered.
as a ML model, it was not covered. As a part of statistics, it was covered. But a small part, very small part.
Markov chain. Sir, we covered
Yeah.
the Markov chain. Yeah.
Only Markov chain, not the hidden Markov one that you'd expect.
Yeah, correct.
No, in the machine learning foundations of machine learning course, didn't we discuss the hidden Markov model?
No, sir.
No, sir.
Really?
We discussed the Gaussian mixture model, not the hidden mark.
Okay. Okay. I think then we can study it today. I think I taught the regular students, but not the 18 batches. Sure. Yeah, so if you come back to the part of speech tagging, these are the different part of speech tags which is typically used for in the NLP, natural language processing. Okay, and these are, if you look at different CD, it is representing some sort of a cardinal number. For example, that's what we saw here. Like 2005 is a cardinal number, so it got a part of speech like CD. And similarly, you have different types of part of speech for nouns also. Like even in NLP, people maintain different part of speech tags as with noun singular, noun plural, like NN, NNS, proper noun, NNP, And for verb also, they maintain different part of speech tags with different forms of the verb. Like verb in its base form is VB. If it is used in past tense, VBD. Then gerund VBG, past participle VBN, etc. So it's not really just you are trying to find out the, if it is a word, it's like a verb or a noun, but also try to get a more fine-grained information of that word, like whether it is a verb past tense, verb present tense, noun proper noun, noun singular, noun plural, etc. So these are the a typical set of part of speech tags that has been used in the NLP domain. And here's another example of how you apply different part of speech tags to a sentence like this. D is a determinant, so DT. The grand jury, where grand is a adjective, right? So adjective is JJ. Jury is a noun. Commented is a past tense verb in past tense form. So it got a part of speech tag like VBD. Okay. So these are the typical way in which people use part of speech tagging to a sentence. So if you look at these examples, okay, what do you think is going to be the part of speech tag of near in this sentence, the near side of the moon?
VB.
The near side of the moon, right? You
Yeah.
think it is VB? Sure. Anybody else? Any other answer?
I mean, it's describing the near side, so probably adjective.
Yeah, probably it is. No, it's an adjective and not a verb, right? It's because it is trying to support the side, right? Which is a
Okay.
noun.
Yeah.
So it's not a verb, but now it is supporting this noun side, so it's a adjective. How about here? They had appeared quite near. They had approached quite near.
No,
Had verb. It's an adverb. Why is it an adverb?
approached is just a verb, so it's extending that.
Mhm.
So that's why.
Sure. It's an adverb. Okay. So how about this one? We were near the station.
Preposition.
Preposition. Why it is a preposition?
So it's basically it's giving the position, like
It's like
we
a
can treat it like
yeah, like the positional. What is the position
Mhm.
to station?
Mm-hmm. Okay, nice. Yeah, that's it. So near need not be always a verb. It can have different, you know, part of speech tag depending upon how it is used. So you are right. First is adjective, then adverb, then preposition. Yeah. Similarly, for example, at all can have different part of speech tag. Yeah. So this is what it is, right? So we are given a sentence, something like time flies like an arrow, right? And let us represent this as the input that is given to us. And the input consists of let's say 5 components, x1, x2, x3, x4, x5, right? So we are given this input x, which is time placed like an array, which consists of x1, x2, x3, x4, and x5. And we need to produce an output y, right? We need to produce an output y. And the y also consists of 5 components, y1, y2, y3, y4, y5. And that each corresponds to the part of speech tag of the corresponding word of the input, right? So if you look at this from a classification point of view, right? You are given some sequence of input, or maybe just you can think of all these sequence of input as a single input x, and you are trying to predict an output y, right? And here, when you are trying to predict an output y, you're not predicting a single label, right? If you when you have learned several classification problems in machine learning or classification models in machine learning, most of them assumes your output y is a it is predicting it is also with a single label, right? Single label y, an element of some 1 to c, where there are c different classes are there, and this y is going to take a value of some k if the input belongs to class k, right? So it is only you are only trying to predict a single output label, right? You're not trying to predict a multiple output labels. But in the case of these kind of problems, like this part of speech tagging or name entity recognition, you have to predict a multiple output labels, right? And there is some structure in that output labels that you are predicting also, right? So you first, your output label consists of some, say in this example, 5 components, and the first one corresponding to the first word, second one corresponding to the second word, etc. Right? So there is a structure in the output labels, and this structure is something like a sequence of output labels, which corresponds to the sequence of input words. And that is what you are trying to predict here. And this has to be treated differently. Why we will see why it has to be treated differently from the standard classification problem. Okay, but this difference is clear, right? Why it is different from the standard classification?
Because of the relation between amongst the neighboring words.
Yeah, so fundamentally, like it's not like you just want to predict one output label, but a collection of output label or a sequence of output labels, right? And
Yeah.
that is how it is different from the standard classification. Okay. Yeah. So in general, these kind of problems. Okay, in general, you can think of your output y. Output y can have some more complex structures. Okay, for example, the output y can be a tree also, tree structure. For example, in NLP, there is this problem called parsing. Okay, so in parsing, you try to identify how different components of the sentences are related to each other, how they are dependent upon each other. What is going to be some sort of a root word, and how it is related to other parts of the sentences. You need to identify that, and to identify that, you form some kind of a tree structure where you have some different nodes, which something like this, where maybe like one word depends upon some other 2 words in this way, etc., etc. So you may form some kind of a tree structure. You will you will learn more about this in the when parsing has when process models are teaches parsing. But you may have to predict an output structure which is kind of a tree structure, not necessarily a sequence structure. So here in this case, you can think of this as some sort of a sequence structure, like this. While the output structures can be even more complex, like a tree or a graph for some other problem statement. So in machine learning, from a machine learning perspective, these kind of problems are in general known as structured prediction, and in more specifically, on specific structure prediction problems, where different labels are depend upon each other in a sequential manner. Okay, the y2 depends upon y1, y3 depends upon y2, etc. in a sequential manner. Like this, in the case of a part of speech tagging, they are known as sequence labeling problem. Yeah, so this is some context of how or why we need a different kind of a machine learning approach to solve these kind of problems.
So does this in the sequence labeling, do we have a fixed number of y values?
So you assume there is, it is upper bounded by some number. The length of the sentence is fixed. In fact, in more specifically in the sequence labeling problem setup, many times people address the sequence labeling by only considering some conditional dependencies, and you can always keep generating or always keep modeling sentences with any length by using that approach. So you don't have to a priori specify a length of the sentence, or many times the models you don't have to know the length of the sentence, because the way they are trying to model things is by just considering some uh, dependencies with its immediate predecessor, which we call as first order Markov assumption, and that way it can work without having to specify a priori the length of the sentence.
So what is the window size that we normally select then? So that becomes a parameter, right? For labeling up one particular, let's say, fifth word in a particular sentence, what is the window we are considering? And because if we are considering, let's say, 7 unique fields for labeling each of the word tokens, so then there will be, let's say, 7 factorial arrangements for basically labeling it. So how we are
Right.
basically
So
reducing
that is why
number of labels.
that is
Yeah.
why we will see these kind of if you are trying to just predict all possible labels, okay, then at once, then the number of different possible labels you may have to consider is going to be exponentially very large, and that kind of approach may not work, and you need to do something else. We will come to that.
And sir, are there like kind of some conditional rules then in that case that okay, this specific family of the words cannot be starting. We cannot start a sentence with the specific family of the verb. Like in this particular sentence that we have on the screen, like cannot be the first word that we can start with in a regular English. Like, do we have that kind of like things also in the sequence labeling problem?
Uh, See, many times you consider some kind of a start token also, and you consider a conditioning with respect to that start token. Okay, so the basic idea is that okay, you you learn some kind of conditional probabilities, and you have some start token, and learn some conditional probabilities conditioned on the start token, then the probabilities associated with some particular tags or some particular tokens will be very, very small. And the probabilities with some other tags and some other tokens will be very large. And that is how you are modeling this situation. For example, you may have probability of a noun given start token will be very large because typically many sentences starts with a noun, right? The probability of something like a verb given start token will be very, very small because in general, the sentences don't start with a verb.
Yeah.
So the models do consider that.
Okay, and specifically when we talk about the sequential labeling problem, those would also be the because ultimately we would be labeling the things as sequential labeling, right?
Yes, so it takes into account these dependencies between different
Okay,
labels, and it make use of that dependency in predicting the next label.
got it, sir. Thanks, sir. Yeah.
So yeah, so if you look at solving this problem, there are so two trivial ways in which we can solve this problem. One is that you just consider this input x1 and try to predict this corresponding output y1. Just consider this input x2. Okay, so when you say input, so here the input is x, which consists of multiple components. So you just consider different components of your input and try to predict its corresponding output. You consider this component x1 and try to predict this output y1, x2, and it produces output y2. Okay, so this kind of point-wise labeling is one way to approach this. Okay, and in doing this point-based labeling, we can use any existing classifiers you are aware of. Maybe neighbors classifier, logistic regression. Okay, any classifier that you are aware of, you can use it. Okay? That is one way to uh, solve this problem. And yeah,
Sir,
this approach
one
obviously
question.
may not be a good approach. Yeah.
The labels that we are talking about, these are like the generic labels, like across all the these are like the standards that we follow in a way.
What do you mean by generic labels?
So basically, like VBZ in a way for being used for the verbs. So I mean, like these are the standard labels that we follow across the NLP standards, or uh, I mean, like these labels are like class specific
So
or like yeah. Yeah.
yeah. So there are so basically there are different uh, part of speech tagging conventions followed, but majorly there are two or three different types of auto speech tagging conventions which are followed. Most of them, yeah, generally consider noun, NN, verb, VB, etc. But there are some in some conventions you may have some more fine-grained categorization of noun or verb, etc. So but there is there is some kind of a uh, so many times all these major noun verb etc are kind of common across different conventions, uh, and there are some so basically from a machine learning perspective, okay, there could be a different data set somebody may have created with some additional labels, for some to represent some words, etc. So when you consider that set of labels to tag, you may have to consider whatever labels one have used to tag the words in that particular data set.
Got it, sir. Okay.
So, this point-wise thing, we did not consider the dependencies between different words or different labels. So that's not going to give a good classification of the words into its corresponding part of speech tags. And the second approach, yeah, maybe, yeah, I think I just. Hmm. So the second approach is to consider the entire all these components of as a single input X, and all these different components of your output as a single label Y, and train a classifier to predict this Y from X. Okay? And so in this case, you are trying to predict the entire Y1, Y2, Y3, Y4, Y5 at once using a model. Now, assume that there is a model which can do this. So see, if you want to apply the standard test classification or standard classification models in this kind of a way, now it will be only predicting a single class label, right? So you need to associate a label with all these different possible combination of Y1, Y2, Y3, Y4, Y5. Okay. So let us assume that our part of speech tag, the number of different part of speech tags that can be assigned to a particular word is something like P. Okay, that is the number of part of speech tags. For example, here, if you look at this table, okay, all these are the possible part of speech tags that can be assigned to a word. Typically, it is that number of possible part of speech tags is something like 50. So typical possible part of speech tags that you can assign to some word is something like 50. So your P is equal to something like 50. And now Y1 can take P possible part of speech tags. Y2 can take P possible part of speech tag. Y3 can take P possible part of speech tag, right? So all these different components can take P possible values. So the number of different classes in total that you have to consider, okay, is going to be, for this particular example, this is going to be P into P into P into P, which is P raised to 5, right?
Yeah.
So if you want to say it as a symbol classification, you need to associate a label with each of these different P raised to 5 possible assignments of classes. Okay. And that number of different classes in this case is then it's going to be very, very large. So now you can think of how much is that 50 raised to 5 is going to be. And generally, the length of the sentence is not something like 5, it can be 10 or 15. And if you consider on an average, the length of the sentence is something like 10. Now, the number of possible classes that you may want to consider is going to be 50 raised to 10, and which is extremely large, very, very large. And many times, many of these classes, you may not even see in the data set. And there could be a lot of issues arising because of that. You may not be able to generalize well to some set of classes. So, this makes this prediction problem extremely complicated. But in this case, you do take into account the dependencies among the different class labels, right? Because you are trying to jointly predict all these labels together at once, right? So you do take into account the dependencies among these class labels. but the number of class labels that you may have to predict is going to be extremely large. Yeah, so so if you recollect your text, simple classification algorithm, right? Let's say logistic regression, right? So in logistic regression, when you use this logistic regression for multi-classification, right? Multi-class classification. So how do you determine that class probabilities? What is that function which is used to determine the class probabilities?
The softmax function.
The softmax function, right? And in the
Right.
softmax function, if you want to
Yes.
predict the probability of some y equal to c given x, where it has a
Question. Sir, can you just explain that part one
differential
more
of
time?
w c transpose x. Explain what?
Sir, can you just explain that part one more time
Sorry?
where you mentioned that 50 to the power 10, like the possible outcome should be if we consider point-wise leveling. Can you explain that part one more time?
Not point-based labeling. The point-based labeling, you are just predicting independent for each of these elements in the input. But this comes up when you try to predict for all the inputs together, right? You try to predict all your outputs y1, y2, y3, y4, y5 for your given input x1, x2, x3, x4, x5.
Oh, there are
Okay.
50.
So when you
So
predict
okay.
this, so now the question is, what are the possible number of classes when if you try to do it this way, right? So for each of these different combination of y1, y2, y3, y4, y5, you have to associate a label, right? So what are the different number of possible combinations of y1, y2, y3, y4, y5? So if each of these component is taking some, you know, so basically in this example, this is representing a part of speech tag. Part of speech tags is around 50. So each of these component is taking 50 possible values. And in this example, we have a sentence of length 5. So now the total number of possible uh, part of speech tags is going to be 50 into 50 into 50 into 50 into 50, which is 50 raised to 5. And that's why you have 50 raised to 5 here. So if the sentence length is something like 10, then it will be 50 raised to 10. So the number of different class labels, okay, if from a classification point of view, from your classifier point of view, the number of different class labels is going to be in the order of something like 50 raised to 10 or so, which is very, very large.
Got
And
it, sir.
it's not only affect the training, but also it affects the inference, right? For example, when you want to predict a class label, say let's say p of y equal to c given x. Now you see in the, let's say, logistic regression, you have to compute this softmax function, right? Exponential WC transpose x to be summation over all, say I exponential of where I is equal to something like 1 to different number of classes, capital C, exponential of W y transpose x. And the number of different classes is going to be in the order of something like 50 raised to 10. So even for inference, this is very, very costly. Okay. So this is the issue in doing either of these approaches.
David.
Yeah, so now we'll see how can we have a very efficient approach which can take into account the dependencies among the class labels also while we want to do auto speech tagging or named entity recognition. Okay. Yeah, so before that we also introduce this a need for a probabilistic modeling in doing part of speech tagging. So so for a given sentence like time flies like an arrow, there could be different part of speech tagging would be possible. One could be this one, where time is a noun and flies is a verb and legs and arrow is in DTNN. So, and this is going to be most plausible part of speech tag which corresponds to this sentence. And there could be another part of speech tag which is possible, something like VB, NNS, in DT, NN, etc. So maybe there could be multiple part of speech tags that could be possible for a given sentence, and we want to have some kind of a probability distribution over these part of speech tags, where you give low probabilities to some of them, high probability to some others, etc. So you can what we are trying to do is something similar to something like what we studied in the case of a Bayesian classifier, right? So uh, or more specific, okay, not the neighbors, but in a Bayesian classifier. A neighbors is a specific case of a Bayesian classifier. You try to model P of, okay, in general for any classification, what you are trying to do is you are trying to model P of y given x, right? And
Yeah.
in a Bayesian classifier, you may model this as P of x given y into P of y divided by P of x. Okay? Or in a generative model, you try to model it as a P of x given y into P of y divided by P of x. And such a modeling is Nabier's classification, right? So in Nabier's classifier, you make an additional assumption that this P of x given y is modeled as product over I equal to 1 to dp of xi given y, right? That is the national Nabier's classifier. But in general, you can call it, you can think of this as a Bayes classifier, where you try to obtain P of y given x using Bayes theorem by applying Bayes theorem, that is P of x given y into P of y divided by P of x. Okay. And the other way is that, okay, you try to directly model P of y given x, right? As we do in the case of a logistic regression like this. In a logistic regression, we try to directly model P of y given x without looking at how P of x given y or P of y is model. You try to get y is given x in this way. Okay? So like in the case of a simple classification setup, we discussed there are two ways to model P of y given x. Okay, ultimately we want a probability distribution over y is given x. So in the case of classification, that y will be just a single class label, but in the case of sequence level, it will be a sequence of outcomes, sequence of labels. So you want to learn this P of y given x, and that can be done in two different ways. Okay, modeling of P of y given x can be done in two different ways, as we have studied in the case of a symbol classification setup. Okay, so one way is generative modeling. P of y given x as P of x y into P of y, hence discriminative modeling.
Sorry, sir, your
P of y
voice is
given
bit
x
breaking
directly
actually.
without modeling x. Okay, without modeling x.
Sir, your voice is breaking in between.
Oh, sorry.
Your voice is breaking, sir, in between.
Okay. Still a issue, still, yeah.
And we're not able to, sir, there is a lag
It's
when,
just breaking, is it?
yeah, it is breaking, sir. And there is also a lag when you are writing something. It's not syncing up with your voice.
1 minute. 1 minute. 1 minute. Hello? Hello, can you hear me?
Yes,
Yes,
sir. Yes,
Yeah.
sir.
yes, sir.
Is this better or same as before? Or worse than
I
before?
think same as before, sir. We're still seeing some breakage. At least I can observe some breaks. I don't know about others.
Okay. Uh,
I think now it is a bit better, maybe.
Yeah,
At
still
least
distortion is there, some
Okay.
distorted, but yeah, better than previous one. Yeah.
let's see. Let's
maybe we
continue
can
and
go
see
ahead.
how it goes.
Yeah. Maybe we can go ahead, and if some problem arises, we'll let you know.
Yeah. But I don't think I have any other solutions right now. We need to stay with that problem.
I think bit
Okay.
better, sir. Yeah, definitely better. Yeah.
Okay, sure. Yeah, so discriminative modeling and generative modeling are two possible ways. And just like in the case of symbol classification setup, now you have a generative model, something like a base classifier. That's an example of a generative model, right? Some one example of a generative model is name-based classifier. And an example of a discriminative model is logistic regression. Right? So similarly, we can develop a generative model and discriminative model for the case of sequence labeling also. Okay, we can develop a generative model and discriminative model for the sequence labeling problems also, where in the case of generative modeling, you try to obtain this P of y given x as P of x given y into P of y divided by P of x. The difference would be that now your y would be consisting of some different number of components, y1, y2, y3, etc., instead of a single component. And that is the major difference. Okay. And similarly, one can develop a discriminative model for sequence labeling setup also, where again y now consists of multiple components, y1, y2, y3, y4, y5, etc. And you can no, there is a generative way of doing sequence labeling, and one of the very popular technique for a generative sequence labeling approach is hidden Markov model, and a very popular technique for discriminative way of doing uh, sequence labeling is known as conditional random fields. Okay. So we look at these two approaches to do sequence labeling, a generative model, which is a hidden Markov model, and a discriminative model, which is conditional random fields. Okay. So you can think of hidden Markov model as an extension of naive-Bayes classifier for a sequence labeling problem, and conditional random fields as an extension of logistic regression model for a sequence labeling problem. So our major issue is how to build this P of y given x. And for that, we can follow a generative approach or a discriminative approach. Hidden Markov model is a generative approach. Conditional random field is a discriminative approach. Now, once we specify the problem, okay, the model, the approach, then the approach will be having some parameters and I need to learn those parameters from the data. And obviously we can follow some existing techniques that has been developed for classification, like maximum likelihood estimation or maximum a posteriori estimation, all that, and estimate the parameters. Now, once we have
I
the
think your
parameters, now
voice
you can make use of this
is
model.
again breaking actually.
Okay.
No, sir, your voice is absolutely fine right now. I think it is individual problem.
Yes, sir.
Okay.
Maybe
Okay, my
sorry
voice is
about
fine now,
that.
right?
Yeah.
Okay, so yeah, so once you learn this model and these parameters from the data, then you can make use of the model for predicting, right? That is basically the inference, right? So we look at this, how each of these stages we will do in the case of these hidden Markov model and conditional random field. So first, let us look at this hidden Markov model. And fundamental idea is that of a generative modeling approach, where you try to model your P of y given x using Bayes' theorem as P of x given y into P of y divided by P of x, right? Now we will see how exactly we'll model each of these different components, okay? How do we model P of x given y? How we model P of y in the case of hidden Markov model, we'll see soon. And once we have this model, then now we can, once we learn the parameters of the model, etc., from the data, we can use this model for prediction, right? For some given x, your correct y, correct part of speech tag sequence is going to be one which maximizes our p of y given x, or max y p of y given x. And you can write p of y given x as p of x given y into p of y divided by p of x. And since the denominator term p of x does not contain y, you can ignore it. And you can write your prediction as max over y p of x given y into p of y. So basically you need these two components, p of x given y and p of y, to perform inference, to predict for a given x. And we will see how exactly hidden Markov models model each of these p of x given y and p of y. Okay. So to just summarize, our x in this case is basically some sequence of words, right? x1, x2, up to some, let's say xk, okay, xt. I'm using this t notation here, xt, and y is the sequence of part of speech tags corresponding to each of these words, right? So it's going to be y1, y2, up to some yt. For a different problem setup such as named entity recognition, this part of speech, instead of part of speech tag, we have something representing a named entity. So in the case of named entity recognition, people use a notation which is called BIO notation. Basically, you need to recognize the named entities in a sentence, right? So for a given sentence, something like these, people sometimes use these named entity tags such as, okay, if some word is the beginning of a named entity, you write it as B. If it is inside a named entity, you write it as I. And if it is outside, that is, if it is not a named entity, you write it as O, right? So that is the BIO notation that people sometimes follow in the case of named entity recognition. For example, for this case, say March 2005 is a named entity, in is not a named entity. So in will be having a label something like O. March will be having beginning of a named entity B. This is inside a named entity I. The is outside O. New is beginning, so B. York is inside I. times. I occurred is outside of, about beginning I. So instead of these auto speech tags, in the case of named entity recognition, the sequence of outputs that you want to predict will be something like this: O B I O B I O B I, etc. Okay. And from that you can figure out what are the different named entities which is present in the sentence. So in general, okay, we consider this situation where our
So can you explain that BIO notation again, please? Once more, please.
so that notation basically is this. O represents any word which is not a named entity, which means outside the named entity. P is representing beginning of a named entity, and I representing inside a named entity, which is
Okay.
all the named entity which is not the beginning one.
Okay. Okay. Got it, sir.
So basically, see New York Times. If you look at it, the new is starting point of the named entity, which is represented by B, and York and Times are in following that. So you write it as II, and Accord is not a part of this named entity, so you write it as O outside the named entity.
Got it. Got it, sir. Thanks.
So there are other format as well, like PLU format as used by Spacey. So is there any effect on the type of the modeling that we model results if we choose different BLU or different formatting, like BLU or this
So there
IP?
will be an effect, of course, and it depends upon the problem, what all information you want to capture from your for your problem that you are trying to solve. So depending upon that, you need to use appropriate notations. And of course, these models are generic models. They can be applied, of course, to any of these sequence labeling problems, irrespective of the notations, but the performance could keep varying depending upon the number of different part of speech labels you have, data you have, etc.
Okay. Okay.
Sir, can B
So
come
here
after
we
I?
cannot. I don't think so.
Okay.
I don't think I can think of a situation like that. Maybe I don't know. Like, if you want, say, if you have like Microsoft, comma, Google, maybe you want to consider
No, but basically if
both
we
these
see
are
that.
different named entities or a same named entity.
Yeah, because I had a doubt because if we see the BLU format, there's just a two special entities that we are assigning, like L for the last and U is the unit. So it is just another form for the I. So by separately, designating them, designating the word tokens, does they really impact our labeling or the NER results?
Obviously, it impacts. All these different notations will be having their own advantages and disadvantages. From a modeling perspective, it doesn't matter. As far as the models that we are looking at, hidden Markov model or they are works irrespective of their labels, but obviously their the performance etc. depends upon all these different labelings you are following. All right, so let's come back to this modeling. So you have x1, x2, xt, which is sequence of words, and y1, y2, yt. It could be depending upon the problem that you are trying to solve, depending upon part space tagging or named integration, you may end up having different labelings. But irrespective of whatever it is, you can think of it as sequence of labels that you want to predict y1, y2 up to yt. So now what we are trying to do is that we are trying to model these two components. How do we model these two components? P of x given y and P of 1. Right? So let's first look at how we will model P of x given y. So what you have here is probability of x1 to up to some xt, e1, y1, y2 up to some yt, right? Now, if you try to uh, model this probability jointly, okay, that is the joint distribution over x1 to xt given y1 to yt, then now then what could be the number of parameters that you may want to end up estimating? Okay, let us bring some notations also into picture. Maybe I have some notations later. Yeah, maybe whatever. So we assume that, okay, let us assume that the number of different possible part of speech tags or number of different tags which are associated with any particular component is something like p as before. Y1 can take p possible values, y2 can take p possible values, y2 can take p possible values. And now, the number of different possible values that can be associated with each of these different components, x1, x2, xt, right? So x1 is representing a word, right? And there could be v words in the vocabulary of a language, and x1 can possibly take v possible words, right? Of course, some of these words will never appearing at the beginning of the sentence, so probability might be very low for that. But if you look at all possible combinations, okay, x1 can take v possible values, s2 can take v possible values, st can take v possible values, right? So given this, how many parameters you may want to end up estimating if you try to directly model this p of x given y?
Sir, can you repeat the question again?
How many parameters do you have to estimate to model p of x1 to xt given y1 to yt?
V into p to the power t.
Sorry?
V to the power t.
Uh, is it only v to the power t?
V into p to the power t.
V into p. V into p to the power t. Why is it so?
Considering these all y's can take p values and v is the corpus, and there will be since it is
So for
to the
each
t.
of these y1 to yt, the number of different possible values x1 to xt can take is going to be v raised to t, right? And how many different y1 to yt are possible? P raised to t different y1 to yt are possible, right? So total number of parameters you may want to estimate is something like p raised to t into v raised to t, right? So that's the total number of parameters you want to estimate. And that's why you said it as, v into p the whole raised to t, right? That's enormously large, quite large. And that is not practically possible for any problem that we want to solve. Okay. So what this HMM assumes is that okay, this is a first assumption that HMM makes in the hidden Markov model. Okay. Now the ith component xi, okay, only depends upon its corresponding label yi. Okay, so if you know yi, okay, which is the label associated with the ith component, and that will give you sufficient information in modeling xi. So this is something like a class conditional independence assumption. Well, okay, if you try to follow the naive Bayes classifier assumption, in naive Bayes classifier, what we do, we assume that, okay, each of these different components only depends upon the class label, right? So now you may, just following what naive Bayes classifier does, you may end up writing this as product over I equal to 1 to capital T, or maybe like T equal to 1 to capital T, probability of xt given y1, y2 up to y capital T, right? So this is the assumption that you followed in the case of an ABS classifier, like different dimensions of X are class conditionally independent, right? Conditionally independent. So you write this as product T equal to 1 to Tp of xt given y1 to yt. And here we can further simplify this, saying that, okay, the teeth component xt only depend upon its corresponding yt, and it does not depend upon other labels y1, y2, or yt plus 1, yt plus 2, etc. You write this as product t equal to 1 to capital T, p of xt given y small t. Okay. So this is the first assumption on modeling p of x given y that is made by a hidden Markov model. So basically, this is what it is. A word appears depending only on its corresponding part of speech tag, and it is independent of other words around the word. So this probability is often called emission probability in the HMM literature, called the emission probability. And this is how it models the emission probability as product of probabilities across each of these different components of your input, conditioned on its corresponding tag or corresponding label yt. Now we'll see how we are going to model this component p of y. So p of
Sir,
y is nothing but, yeah.
sir, sir, one quick question. Sir, you mentioned that a total number of parameters should be VP to the rest of power T. So can you explain that part one more, that how you are getting that VP to the T?
Because no, here when you are trying to jointly model all x1 to xt given y1 to yt, for a particular denominator y1 to yt, how many different possible numerators could be there? So if you assume x1 take v different values, x2 take v different values, xt take v different values, so the number of different possible combination of x1 to xt is going to be v raised to t.
Right, for particular y1, maybe
So,
for particular y, yeah.
For a particular y1 to yt. And how many different possible y1 to yt are there?
It's p to the power.
If you assume, yeah, that is going to be p raised to t.
But sir, this is against
So,
of the we are considering for Markov, hidden Markov, right?
This is not for hidden Markov. We are talking. I was talking about
Yeah.
jointly modeling. The issue with jointly modeling x1
Oh,
to xt. for a given y1 to yt.
Got it, sir. Then that was the confusion. Yeah, got it. Yeah. Thank you, sir.
Yeah. So that's going to be vp raised to t. So that is the reason why we need to make some assumptions and simplify this model to reduce the number of parameters you want to estimate.
Yes, sir. Right.
So now coming back to the same question. So if you make this assumption, how many parameters do we have to estimate now? We made this assumption that, okay, p of x given y can be written as product over t equal to 1 to t, p of xt given yt. And now, how many parameters do we have to estimate? See, let us assume that, uh, you know, uh, the modeling of p of xt given yt does not depend upon the position t, okay? And this model p of xt given yt is same across all the positions t equal to 1 to t. In which means we just need to learn one model p of xt given yt. And if we just want to learn p of xt given yt, how many parameters do you need?
V into P.
So we take p values, we take v values, x take v values, so it's going to be v into p, right? So even in case you assume having a different model for each of these different positions, like you assume that the parameters of the model are going to be different for different positions. If you take even that into account, then it is going to be something like t into v into p, right? So the number of parameters is much smaller compared to what we had before if we make these kind of assumptions. Now coming back to the modeling of y, p of y. So p of y, the way they model. Okay. So let us know what happens if I make a IID assumption on modeling p of y. No, that means if I assume that all these p of y1. Okay, first of all, uh, now if I want to jointly model p of y1 to yt, how many parameters do I need?
Sorry, sir. Come again, please.
If I want to jointly model p of y1 to yt, how many parameters do I need?
P raised by T.
So p raised to t parameters I need. So that's very large. So I need to make some simplifying assumption over this. And maybe now I go for the most simplifying assumption. Let's say I write it as product I equal to or t equal to 1 to capital T, p of yi.
Mm. Yeah.
Now, if I make this simplifying assumption, okay, I can reduce the number of parameters. Okay, I can reduce the number of parameters. But
Yeah.
will it capture the dependencies across different positions?
For different positions.
So I want to somehow capture the dependencies so I can predict better, right? But if I make this kind of a simplifying assumption, my final model will be something like if I look at p of x given y into p of y, it is going to be product t equal to 1 to t, p of x t given yt into p of yt, right? And I am trying to do an arc max of y1 to yt. product t equal to 1 to t, p of xt given yt into p of yt. So is this any better than doing a point-wise prediction? Is it any better than doing this point-wise prediction? Point-wise prediction means this, right? This is what we have explained as a point-wise prediction, where you just predict for each of these components separately. Look at x1, predict y1. Look at s2, predict y2. So that is point-wise prediction. And if I model this in this
But
way,
with the IID, we are not doing the point-based prediction, right?
sorry,
With the IID assumption, we have taken away that
Hmm.
point-based prediction, right?
with the IDS, we are going back to point-wise prediction. Is that what you are saying?
No, I'm saying the other way around. We are going away from that in a way.
No, point-wise prediction is what
Oh, sorry.
we
Yeah,
are
yeah,
predicting
yeah, yeah, yeah.
for each of these components separately,
Correct.
right?
Yeah, that is what exactly I was saying. So yes, with the IID prediction, we are going back to this. Yeah.
So we are going back to that, right? So argmax over all these, you can simply write it as argmax over each of these components, like argmax over y1 p of x1 given y1 into p of y1, argmax over y2 p of x2 given y2 into p of y2. Like that you can write. Where you know each of these can be seen as doing a point-wise prediction using a naive-Bayes classifier. Okay, so you see when you go for that assumption over y, p of y to be written as product over y1 to product over t equal to 1 to t p of yi, then we are back to point-wise prediction. We we won't be able to capture any dependence among the different labels. So we don't want to do that. We want to somehow capture the dependence also. So instead of considering a independence across yi's, you assume that there is a dependence. So y2, the second label, will depend upon the first label y1. y3, the third label, will depend upon the second label y2, and like that. So you can write p of y1 to yt as product equal to 1 to t p of yi given yi minus 1. Sorry, p of yt given yt minus 1. Okay, so when you try to model some probability distribution over a sequence of random variables, okay, by assuming the ith element in that sequence only depend upon the I minus 1th element, then that is a kind of an assumption that you are making over your sequence, like how they are depending upon each other. And this is something called the first order Markov dependence. Okay? First order Markov assumption. So if you simply look at the joint distribution over y1 to yt, ideally you can write it according to chain rule as something like p of y1 into p of y2 given y1, p of y3 given y1, y2, p of y4 given y3, y1, y2, y1, etc. Right? But you assume some kind of uh, a simplification to this dependency, okay, where you assume that a particular label only depend upon the previous label and not the labels before that. And that is known as the first order Markov assumption. And you can write this as p of y1 into p of y2 given y1, p of y3 given y2, etc. Right? So this is known as a first order Markov assumption. For example, if you make assumption that a label depends upon previous two labels and not the ones before that. In which case you write it as P of y1 into P of y2 given y1 into P of y3 given y1 y2 into P of y4 given y3 y2 into P of y5 given y4 y3. That is known as the second order Markov assumption. So a hidden Markov model make a first order Markov assumption over modeling of these sequence of labels, and you write it P of y component as something something like this: product t equal to 1 to t, yeah, this, right? Product t equal to 1 to t, P of yt given yt minus 1. So now this is not the same as doing a point-based prediction. Now, if you go back to this, here you will be having the second component, like P of yt given yt minus 1. So, which tries to capture the dependencies among the labels. So you cannot just factorize these across different components and predict independently. You will end up considering the dependencies among the labels also in predicting your outcome y. Okay. So this is how the hidden Markov model is trying to capture the dependencies among the different elements in the sequence through y, by saying that different elements in your tag sequence depend upon each other in a first order Markov assumption manner. Okay.
Yes.
Yes, sir.
Yeah. So now if you try to infer your credit y cap for some given s, then you consider it as argmax over p of x given into p of y, which is product t equal to 1 to t p of xt given yt into p of yt given yt minus 1. And this somehow capture the dependence among the different tags in predicting your outcome y cap. So now if you look at a graphical model representation of say a hidden Markov model, okay, so this is how it looks like. Okay, so a graphical model representation generally consists of some representation of your probability model in terms of some circles which represents the random variables of interest or the entities of interest to us, and how these different entities and random variables are depending upon each other, right? So if you look at a simple name-based classifier, okay, in a name-based classifier, you model P of y given x as P of x given y into P of y, right? So the x's, your input, depend upon y, right? So you often have, if you represent your x by this circle and y by this circle, so the dependence is modeled like, okay, x depends upon y, so there is an arrow from y to x. So this is how you consider a graphical model representation of your probability distribution or the probability model that you are assuming, where you're trying to represent the probability model in terms of graphs, in terms of some nodes representing the variables and edges representing the dependence between these variables, right? So here you will be considering some directed edges, which captures the dependence between the variables. They're also known as Bayesian networks, okay? These directed probabilistic graphical models. So
they are P of x given y, right? Or these graph.
Yeah, this represents P of x given y into P of y.
Hmm.
So this is for a simple name-based classifier. Now, in our case, we are looking at the sequence labeling problems where we have some sequence of x's, x1, x2 up to xt, and sequence of y's, y1, y2, yt. So these forms, okay, these are the different variables of interest to us. We are trying to define a model over these sequence of inputs x1 to xt and sequence of outputs y1 to yt. And we have defined how to model this, right? We have defined our model. Our model is something like uh, product t equal to 1 to t, p of xt given yt into p of yt given yt minus 1. Okay? So if you try to go for a graphical model representation of this model, which is basically a hidden Markov model. So this is how you can see the graphical model representation is looking like. Okay, all these are representing your different components of x, x1, x2, x3, x4, x5 like this, and these are different components of y, y1, y2, y3, y4, y5, and your x1 depends upon y1, which is modeled by having an arrow from y1 to x1, and typically, no, this is the case. This is repeated across all your x2, y2, x3, y3, etc. Right? x2 depends upon y2, so we have an arrow from y2 to x2 like that. And now, if you look at the dependencies among these y2s, I mean y variables, elements of y, it is like, okay, there is y2 depending upon y1, y3 depending upon y2, y4 depending upon y3. So you have an arrow from y1 to y2 capturing the dependence, y2 to y3 capturing the dependence, like that, right? So this is the graphical model representation of a hidden Markov model over different components of your input and output. And these components that you see here, yeah, these are observed in your data, right? And you, yeah. So yeah. But I will go to that later. But this is a graphical model representation. Is it clear?
If
So now, so when I want to perform inference, I follow this model that I have just defined, right? So if I want to predict the probability of for this particular example, I want to predict the probability of y I am considering as something like n BBZ IN DT NN, right? The probability of this sequence of no probability that what's the probability that I get this sequence of facts as my prediction outcome given the input time, price, like, and arrow. So I compute this probability according to my hidden Markov model as probability of noun, probability of NN into probability of what? Probability of?
VBZ,
Okay, if you want to write it that way, yeah. How do you write probability of VBZ?
you, VBZ given NN
VBZ given NN into
into P of IN given VBZ.
in given VBZ into
dt given in. Sorry,
P of dt given in.
dt given I, yeah, and then nn given dt.
NN given dt.
into
Into
Time given and
into I have probability of time
given
given
in.
nn
Okay.
into
Time given VBZ.
into
Into
VBZ.
phi is given
VBZ.
into
A lie given n.
like given nn probability of
And given
n
dt.
given dt into probability of
Arrows given difference.
arrow given nn.
And then
So this is how I find out the probability. Okay.
mm,
So this is not exactly probability because I have, I have ignored that denominator term because I don't want that denominator term in finding out which sequence of tags will get the highest value. Okay. So this gives you some value, no, and I can, if I want to find out, okay, what is the right sequence of tags, I can try to find these values across all possible tag sequences that can be assigned to time flies like an error and choose the one which gets the maximum value, right?
The last statement, please. One more time, please.
So if I want to predict what is the tag sequence that needs to be assigned to this sentence, time flies like an arrow, I can compute this probability. Okay, I can compute this across all possible assignment of tag sequences, and then I can choose that tag sequence which gets the highest probability, right?
Yes.
In fact, by this we are not exactly computing probability because we are ignoring this denominator term, right? Because we don't need that denominator term in finding out the best possible tag sequence. So what this gives you is just some likelihood that is associated with all these different tag sequences. So what you do is that I choose that likelihood which has the maximum value across all the different tag sequences as my final prediction. Okay. Yeah, so that's how I do inference based upon this model, right? Any question?
Yes, sir. So during inference time, let's say we are predicting on the unseen data, we would not know the Y's upfront. So how does one
Right.
calculate? Yeah.
So that's how that's what I said now, right? You consider all possible Y's tag sequences and you compute this value for all possible tag sequences and choose that tag sequences which has the highest value.
Okay, got it. So,
but then, is that feasible?
I think the number
Is
of
that practically
combinations would then explode. Yeah.
Yeah, the number of combinations would be very large, right?
Yes, sir.
Again, the number of different tag sequences you need to consider is in the order of p raised to t, right?
Correct. Yeah.
And you need to compute these values across all the possible p raised to t combinations, which makes the inference very, very slow, right?
Yes,
But
sir.
fortunately, this structure of this hidden Markov model has assumed, the structure the hidden Markov model has assumed provides us a way to perform this inference very efficiently. In fact, we will see that soon. Okay, we'll see that soon. We can perform this argmax, and performing this argmax does not require us to evaluate across all the p raised to t possible tag sequences. Instead, we can do it just performing some p square into t operations. Okay, we don't have to perform p raised to t operations to find out the best tag sequence for a given input, but we can perform it in p square t time, and p square t is very reasonable. It's not a large number, right? P square t is very reasonable, and the inference can be done very, very fast. We will see that soon, how to do that, how to do inference faster without having to enumerate all the possible tag sequences by making use of this structure of the model, right? The hidden Markov model's assumption allows you to do that. So yeah,
Sure.
and there is a algorithm people have developed to do that, which is a very popular technique known as Viterbi algorithm. Okay, and we'll just have a look at that Viterbi algorithm soon. Yeah, but now before applying performance, before you are capable of doing performance, you need to know what's the probability associated with each of these components, right? What's the probability of VP given NN, probability of IN given VP probability of DT given IN? How do you learn that probabilities? Also the probability of time given NN, size given VP life given NN, and given DT. Okay, how do you learn those probabilities? So in order to learn that probabilities of if you need data, and you need a labeled data, and there are some part of speech tagged data available. Very huge part of speech tag data is available, and you can make use of this part of speech tagged data. I'm not sure if Brown corpus is part of speech tagged. Yeah, but there are several part of speech tagged corpus which are available, and given this corpus, so in corpus, when you say part of speech tagged corpus, so somebody may have labeled each sentence with its corresponding part of speech, right? So given such a corpus, we can learn each of these probabilities by enumerating, by computing the number of times these combinations have appeared, right? For example, if you want to compute p of xt given yt, that is something like probability of time given nn, what you do is that you look at this corpus, find a number of times xt and yt has appeared together. For instance, time and noun has appeared together. That is given by c of xt yt. And you find number of times yt is appearing, which is given by c of yt. And you can get this probability by dividing c of xt yt divided by c of yt. That is number of times where xt is annotated as yt divided by number of occurrences of the tag yt. And similarly, if you want to find out p of yt given yt minus 1, you look at the corpus and find number of times the sequence yt minus 1 is yt minus 1 yt is appearing, number of times yt minus 1 yt sequence is appearing, and that divided by number of times yt minus 1 is appearing, and that will give you, right? For example, if you want to compute the probability of VB given NN, you look at number of times in the corpus NN VB has appeared, and you divide that by the number of times NN is appearing, and that will give you this conditional probability of yt given yt minus 1, right? You can compute these conditional probabilities from a part of speech tagged corpus. Okay, so that's this way of computing these conditional probabilities is also known as the maximum likelihood estimate of the probabilities. And many times, you don't just simply rely on this number, but you also do some kind of a smoothing. Okay, most likely Professor Mananda will talk about smoothing in some class. But the idea is that, okay, you add some pseudo count to this so that you avoid cases where the values are zero. Okay. But you can possibly, you can get these probabilities from your part of speech tagged corpus.
Sir, can you just explain this last part, px of t y t, that one more time, please?
P of xt given by t is probability of xt given, okay, which is, for example, here, probability of time given nn, right? So which means that, okay, out of total number of times nn is appearing, how many of number of times time is appearing with nn, like,
Yeah.
So that you can find out from the corpus by counting the number of times time and nn is appearing, that is given by c of xt yt divided by number of times nn is appearing, which is given by c of yt.
Okay. And this all is then basically based on the corpus that we have for our learning purpose, basically.
Right, yes.
And the same follows for the yt given yt minus 1?
Yes, same follows for yt given yt minus 1 also. Yeah, this is how you learn the parameters. So now, yeah, so this is this inference. Once you learn the parameters, that is, once you learn the model, now you can perform inference. You can predict for any given x, right? And the way you predict for any given x is by doing an argmax over y, product over t equal to 1 to t, p of xt given yt into p of yt given yt minus 1, right? And now the issue is, the number of different y's that you want to consider could be very, very large. Okay, of course, one of these part of speech tagged data set is called Penn tree bank data set. And in Penn tree bank data set, the number of different part of speech tags they are considering is around 36. Okay. And so, if hmm, uh, if your sentence length, okay, is something like t, and if the number of different part of speech tags in the corpus is something like, this is y, okay, then the number of different y's that you have to consider here, right? The number of different y's that you have to consider here is going to be something like y raised to t, right? And now if you consider is sentence of length 6, it just is sentence which containing like 6 words. This is going to be something like 36 raised to 6, which is very, very large. And for a short X sentence, this is going to be very large. And just enumerating this over all your possible tags, which is this many number of tags, is practically not possible. So how can we improve this? Okay, how can we improve this? So we can improve this by making use of the structure of the probability model that is given by the hidden Markov model. Okay, and the idea is okay. Well, there's an algorithm which has proposed to perform inference efficiently for a hidden Markov model, which is known as the Viterbi algorithm. And this algorithm can perform this inference because of y square t time, which is a huge improvement over what we have here. And this algorithm is based upon something called the dynamic programming approach. But basically, the idea is very simple. Okay? So let me do one thing. Before getting into this, let me just write this down. So this is what we want to do, right? Let us assume that our sentence length is, let's say, the sentence length is something like 3. Okay. So I'll be having an output like 3 component output. So I need to do some arg max over y1, y2, y3, right? Of the probability model that I have, which is like probability of y1 into probability of x1 given y1, probability of y2 given y1 into x3, x2 given y2.
Yeah.
Into probability of y3 given y2 into probability of
x3 given y3.
y3. Yeah. So this is, I need to do an argmax over this, right?
Yeah.
So now what I can do is that I can bring the maximization inside this product, because these components does not depend upon y3. y3 comes into picture only here, and then y2. Okay, so then these components does not depend upon y2. Okay, so y2 will come into picture only from this component onwards, right? From this component onwards, only y2 will come into picture. So what I can do is that I can bring these part maximization over each of these components inside the product. So for instance, I can write this as something like this, right? Okay, I first do a okay, and maybe I can do this. No, I can do an arg max over y3, p of y3 given y2 to p of x3 given y3. Okay, and then I can write p of x2 given y2 into p of y2 given y1. Okay, and then can perform an arg max over y2 here, because the components before this does not have y2, right? So I can do an argmax over y2 over all these terms, and then I can have an argmax over y1, p of y1 into p of x1 y1 y1, this component. No, because of this some first order Markov assumption, independence assumptions, not completely independent, but first order Markov assumption. It provides a way to perform this argmax operation efficiently by allowing to bring this maximization over these components inside the product. Okay, So, and no, is this clear? Is this step clear?
Yes, sir.
Yeah. So now when you take this maximization over y3, okay, so this is basically when you take the argmax of this y3 over p of y3 given y2 into x3 given y3, okay. So this is now this is now just going to be a function of y2. You can write it as something like psi of y2, right? For different values of y2, you can find out what is the what is the value of y3 which maximizes. Okay, what's the value of y3 which maximizes p of y3 given y2 into p of x3 given y3. Okay, so this is basically a function of both y2 and y3, and now this argmax operation you perform over y3. So you only need to keep that value, that value for which y3 is maximum for different values of y2. Okay, so you can.
Sir, how are we saying then the first part that it only depends on y2? It even that is also like y2 argmax of y2 is also dependent on y3 in a way, right? Because
So you
it
see
it
this.
com yeah.
So you see this bracket is starting from here until here.
Hmm.
The bracket covers that. So that's why I wrote it as a function of y2. This so so here what you're trying to do is that you are only trying to find out an argmax over y3 for different values of y2. At this point, you cannot find out. You cannot say, okay, this is my this is my y3. I cannot say that because no, the y3 that I should choose eventually depend upon what is that y2 I have chosen. There is a dependence. But what I'm saying is that no, you no, you don't have to perform this compute this y3 for all these different values of y1 and y2. Okay, but you can perform an argmax operation separately over these components, where you find out for each of these different values of y2, what is that value of y3 which gives maximum, right? Okay, so you have now a function of y2, some psi of y2, and psi of y2 is obtained by finding out that value of y3 which would maximize different values of y2, and you maintain a table. You separately maintain a table. Okay, this is the value. This is the value of psi of y2 that you have obtained by maximizing over y3, and this is that y3 which has maximized it. Okay, so at this point, I may not be able to decide, okay, this is my y3. I cannot decide that. That will eventually depend upon what y2 I will choose, right?
Yeah.
But no, I can maintain it. I can do it in a sequential manner. I can do it in a sequential manner where now I perform this argmax over y3 first, maintain this table where I have some, I maintain, okay, for different values of y2, what this is going to be. Okay. So I have some psi of y2 obtained as a result of performing argmax over these components. right?
Mm.
And now what I can do is that I can consider this P of y2, P of x2 given y2 and psi of y2 and perform an argmax over y2, right? I can perform an argmax over y2. Okay. So what I'm trying to do is that where is my y? Y1 is there. Yeah. So I can do a perform an argmax over y2, right? So what I'm trying to do is that I'm trying to find out, okay, if we consider these components, okay, and when I perform this argmax over y2, I will end up getting a function of y1, okay, function of y1. That is, for different values of y1, I will get some value which is obtained by doing an argmax over y2. Okay. Again, at this point, I may not be able to choose what is my y2 is going to be. Okay.
Correct.
What is my y2 is going to be depend upon what I eventually choose as y1. But I can maintain this table or this sequence of values. Okay, this function. For which what is the different values you get for y1 by and that is obtained by doing an argmax over y2. So if you do an argmax over y2, what are the different values you are going to get for y1? Okay, and now what I can do, I can combine this psi of y1 with p of y1, p of x1 given y1, and do an argmax over y1. Okay, so this will this operation argmax over y1, p of y1, x1 given y1, and psi of y1 will allow me to choose an optimal value of y1, right? So this will help me to choose an optimal value of y1. And now what I do is that I can now backtrack. Okay, so I can now go back to this function and I can see, okay, if I had, eventually if I have chosen this, after this argmax operation, let me assume that I have chosen y1 cap as the optimal value of y1. So for that y1 cap I have chosen, okay, I can go and find out what is that y2 which has given me
Y1 cap.
okay for what y1 cap that I have chosen. For that y1 cap I have chosen. Now what is that? What is that value of psi of y1 and what is that y2 which has given me that psi of y1, right? Sorry, not psi of y1, psi of y1 cap. Okay, so that y2 corresponding this this psi of y1 cap. Oh, okay, so you have this psi of y1 cap and you have this some value associated with psi of y1 cap, right? So what is that y2 that gave you that value, and let that be y2 cap. Okay, so that will give me my that y2 cap, and now I can go back to this function and find out what is psi of y2 cap and what is that y3 which gave me that psi of y2 cap, and that will give me my y3 cap. And now this is what my final tag sequence, y1 cap, y2 cap, y3 cap, and that's going to be my final tag sequence. Got it. Final output. Okay, so this is very simple approach. Okay, I mean just making use of the structure of this probability model by bringing the max operation inside. One can efficiently perform this inference, right? In a step-by-step manner, in a sequential manner, right? And this is what the Viterbi algorithm does. Okay, this is what the Viterbi algorithm does. In a sequential manner, in a step-by-step manner, it try to find out the optimal tag sequence. And no, see if you look at no, if you look at this particular operation that you have here, which allows you to form this table psi of y2, or what to say, function psi of y2. No, what you had to do is that you need to evaluate this. Okay, for each value of y2, you need to perform an argmax over y3, right? So, no, according to our previous assumption, that is number of different possible part of speech tags. If we assume the number of possible part of speech tags to be something like p, okay? So for each value of y2, I need to perform this argmax over y3. So there are p operations involved in finding out an argmax over y3 for each value of y2, and y2 take p different values, right? So to compute this psi of y2, I need to perform p square operation, and I am repeating the same thing when I am trying to find out. No, I am trying to perform this argmax over y2, right? And when when I in forming this psi of y1, when I want to form this psi of y1, I need to perform this argmax over y2. Y2 take p different values, and y1 take p different values. So the number of operations I need to perform to obtain psi of y1 is again p square. And then again, I need to perform this argmax over y1. Again, no, yeah, this argmax over y1 can be simply done in p steps, right? Or does it require p square? It doesn't require p square, right? It is just
It should be p square, sir, right?
why is it p square? I just need to argmax over y1, right?
Yeah, and y1 can again take p values. And then for
that's all right. That's all right. P. Isn't it? What do we need to do p square there? No, right?
okay. This was the first term, right? Yeah. P1,
The first
y1.
term.
Yeah.
Yeah. So no. So if you look at the number of operations required, it is going to be something like
P raised to the power 5.
P raised to 5. Why? We don't need p raised to 5. We are no p square. We are doing this first, which is p square. Then we are doing computation of psi of y1, which is taking another p square. So it's not p square into p square. It is p square plus p square.
Oh, okay. Yeah.
So p square plus p square. Okay, I can just write it as up to t up to t. P square plus p square up to t, which is equal to some t into p square. But for the first one, you don't need p square. You only need p. But no, it doesn't hurt to write it as t into p square.
But then, sir, how did we write the third p square then? I mean, like
that's not third p square. It is just p square plus p. But no, it is t minus 1 into p square. But it is, you can simply write it as t into p square. That's short.
Okay. Approximation.
See what happens. So why we need a t into p square is because many times you consider the start symbol also. Okay. So there will be one more additional conditional that you have, which is condition with respect to the start symbol. But that's okay. Don't worry about that. But it's in general, you can think of it as t into p square. But this operations is clear, right? The sequence of operations which are involved.
Sir, I have one doubt in backtracking. Like once, how we calculated y cap? Is it like when we were going forward pass, are we storing those values so that once we have y1 cap, we can calculate y2 cap?
So you maintain this table, right? Where
Mhm.
for different values of y1 cap, what are the values as well as which is that y2 which gave you that value. So you also maintain that y2 which gave you that value.
So what will be the size of the table? I thought just one maximum value we are storing in that table as a function of.
You may want to store that y2 also in order to allow you to backtrack. Okay, you may have to store that y2 which gave you that value also.
Okay, and one more doubt I have, like why initial is only p, like others were p square?
Because here what you're trying to do is that if you just look at this Armax operation, this Armax is only p. But then you are trying to do this Armax over y2 for different values of y1, right? That is why you need p square here. But here there is no such thing needed because there is no previous label.
Oh,
This is the
okay.
start label. You just need to do an Armax over y1, so it just requires p.
Okay, thank you, sir.
Okay, so is this clear, like how these p raised to t can be reduced to something like p square into t by bringing these argmax inside the product? So in general, in probabilistic graphical models, people consider these kind of efficient way to perform inference. Okay, many times when you want to do prediction, you need to do some argmax over y p of y. But depending upon the way you model p of y, you can bring this max operation inside and you can perform efficient inference. So this is often known as max product algorithm in a general sense in probabilistic graphical models. And specifically for sequence labeling problems, we call it as Viterbi algorithm. Well, the sequence labeling models are not only used in natural language processing, but also used in speech processing. And as I understand, this hidden marker model have been first introduced for speech processing, and the Viterbi algorithm has been developed for speech processing, and which later has been used in natural language processing also. Okay, so here in this example that we have considered, I performed this max argmax over y3 first, and then I performed it with respect to y2, and then I performed with respect to y1. You can think of doing it in the reverse direction also. You can think of first doing it with respect to y1, right? And then you can think of doing it with respect to y2, and then you can think of doing it with respect to y3. Okay, in the reverse direction also you can think of doing it. And this Viterbi algorithm that we are going to discuss is doing it in that order, where you first maximize with respect to y1, and then you maximize with respect to y2, then you maximize with respect to y3 in that way. Okay. So there is a change in the yeah. Um, so
Sir, just
yes.
maybe this might be a very naive question, but remember when we used to have the IID assumption, we used to go ahead and take the logs for the sake of simplicity of the calculation. But because here we are using the first order assumption, is that the reason why we are not going with the logarithmic?
Uh, Not really. No. So uh, see there, you use log for doing the maximum likelihood estimation, right? You don't use log in doing inference. So in doing the maximum likelihood estimate, that is in finding out the parameters, you consider the log likelihood and perform do estimation like minimization of that log likelihood and estimate the parameters. So this we estimate the parameters here. Okay, the way you estimate these parameters here. So this can be seen as a result of taking log and equating to 0 because this is nothing but the maximum likelihood estimate. Okay, this way of estimating this is nothing but maximum likelihood estimation. Okay, and this can be seen as a result of taking log and equating it to 0 and getting these estimate of the probabilities. But in the case of inference, we generally do not take. But see, I mean, we can take log also in the standard setup. It is just one scalar value that you consider, and there is no products involved. Yeah, in the case of Viterbi, there is products involved, and you can take log over this also. No, it's just become log. It is just the whole idea just carries over. So you have this sum of the terms instead of product of the terms, and you can bring this max inside the sum instead of doing this max inside the product.
Yeah.
So there is equivalently you have instead of max product algorithm, max sum algorithm, but the idea remains the same. You just bring this summation inside you just bring this maximization inside the summation instead of bringing the maximization inside the product.
Yeah, yeah, and I mean, like from the mathematical computation point of view, because we used to make things easy then, so that's where this thought just came. I'm sorry if it caused a confusion
From
also.
the computational perspective, no, there's no difference, but definitely from the numerical perspective, it can it can help.
Yeah.
There can be avoid some numerical instabilities when you take the summation instead of product. Yeah. Yeah. So you can think of Viterbi algorithm to consist of these different steps. Okay. Okay. So in this Viterbi algorithm, which is described here, so Aij represents the transition probability, the probability of transitioning from ith label to jth label, right? So basically, this is your you have this y2 y1, right? Okay. Probability of y2 y1, which is basically also known as the transition probability, as we have mentioned here. This is the transition probability.
Yeah.
So the algorithm which is described here, this Aij represents the transition probability, which is something representing probability of yj given yi, and bj represents emission probability. That is here the observations are denoted by O, O1, O2 to instead of X. Okay, in this algorithm, the observations are denoted as O, O1, O2 up to some ON. These are observations which correspond to in our notations that we have seen so far, x1, x2 up to xn. So bj is the emission probability, like bj of o, let's say bj of O2 represents probability of O2 given Yj. Okay, this is the emission probability. And no, so the idea is similar to what we have discussed. So in the algorithm, so in what I have discussed, I started from the last, performing an arcmax over Y3 first, and then moving on to performing an arcmax over Y2 and then over Y1, etc. But in the algorithm, they are doing it over Y1 first. So you perform arcmax over Y1 first, maintain a table of psi of Y1, right? And then you combine that with uh, this P of Y2 given Y1, S2 given Y2, etc., and perform an arcmax over Y2, and you keep going in that way. That's what is how is described in the algorithm. Okay. So yeah, so uh, yeah, so you maintain only like Vt minus 1i. Okay, so Vt minus 1i is something that you have obtained from the previous step, okay? Like this psi of y1 that we maintain, and you combine that with the transition probability aij, that is O2 given y1, and emission probability pjot, which is this x2 given y2, and perform a maximization over all the i's, okay, and that will give you some VTJ, and the meaning of this VTJ is this, okay. So VTJ is the probability that you are in state J. So state J, or state J basically, okay. So many times when people discuss this hidden Markov model, they consider transitioning from one state to another, where state is nothing but this output, that label that is associated with the problem that we have. So in our case, so we have some three different part of speech tags, right? And I think there's some. Yeah. So you can think of this transition here. You start with some start state, and from start state, at the end of first step, you may move to a state. A state is nothing but you can think of that tag, the label that is associated with the first word, and then from there you move to the label associated with the second word, and then from there you move to the label associated with the third word, and finally now you end. And while you are in any of these states, you can think of obtaining your observation by uh, using the emission probability matrix, right? So, so this is nothing but this basically the hidden Markov model consists of the transition probabilities and emission probabilities, right? So you start with some start state, and then you obtain. So if you so you get your P of y1 from some start state, and then you get your P of y2 based upon this y1 condition on this y1, right? and then you get P of y3 conditioned on y2, etc. Right? So this the sequence in which you are trying to model your P of y is often represented as transitioning from one state to another. So each state corresponds to the label that is associated with some word, right? So from a start state, you go to uh, y1. Now y1 could be verb, or y1 could be something like to. And now from this y1, you have a probability distribution over some possible labels. Okay. So if your y1 is 2, then from there you have a probability of moving to a noun state, or you have some probability of moving to verb state. Okay. So from this you may either move to noun state or verb state, and that forms your third state. And from there you may again either move to to state or noun state, etc., etc. And each of these different labels correspond to some states. And at each state, while you're in each state, you have some uh, probability also associated with the words that you observe. So you have a probability of predicting some word like artwork or race, the, to, etc. at each of these states, which is the emission probability. And this is the transition probabilities. So in the Viterbi algorithm that you are discussing, this Aij represents the emission probabilities. Like A24 represents probability of moving to end label from a label like to, and here A21 represents probability of VB given to, A12 represents probability of 2 given VB, right? So all these AIJs represents these transition probabilities that you have. And the emission probabilities are represented by something like PJOT, right? So OT, these are your OTs, and uh, 2 is represented by J, the Jth state. Okay, so if you're in Jth state, what's the probability of predicting all these different words that is determined by PJOT, which is basically modeling P of xj given xt given yt, what we had in the previously. So this is the notations that is used to understand the algorithm. Maybe, yeah. Yeah. So whatever VTJ that you are computing here, the VTJ that you are computing here is basically representing the probability that see, assume that you have some total n observation, 1 or 2 up to some or n, right? And you you have seen some O T observations. Okay, so on to OT observations, and no, after seeing the first T observations, and after knowing the most probable tags, okay, which is okay. I think I have to use so many different notations here. Okay. Are you following these notations?
That diagram we understood, sir, where the transition probability and omission probability. But here, what is this BJ in this formula? AIJ, it's the transition, but in BJ there is in bracket OT. So is it like BJ is function of OT? What is that?
Okay, let me see if I have something else to. minute. Yeah, I don't have any other. Yeah, I think. Yeah, what is your current state, mental state? Do you like to continue discussing this further, or we discuss this another time?
To be very honest, sir, if I mean, like, we were able, I mean, like, at least I was able to follow you perfectly up to the previous slide where we discussed the foundation. But from here, I'm a bit lost. But yeah, this is just to me, I think.
Okay, let's do one thing. Let's discuss the Viterbi algorithm sometime later. I'll just try to do one thing. I'll just cover the conditional random field. Okay.
Sure,
But you got the essence of Viterbi algorithm, right?
Yes, sir.
What it is, right?
Yes.
Yeah. So
Yes,
we
sir.
will cover the details of the Viterbi algorithm later, and let's just discuss another discriminating which is used for sequence labeling, which is known as the conditional random field. Okay. Yeah. So now what could happen is that now, so when see if you are using hidden Markov model, you can see that you want to exactly model this p of xt given yt, right? Where xt is you are assuming it as a word and yt is a label. Okay? So many times you have to encounter situations where you have seen some at the test data you have words which you have not seen at the time of uh, training data at all, right? You train your model based upon some training data, you get these probabilities based upon some training data, and many times at the test time, we deploy all these models in practice somewhere, and now at the test data, you may see a lot of words which you have not seen at the training data, right? For example, many proper nouns, you may end up seeing some new proper nouns at test time which you have not seen in the training time. Okay? But even though you may use smoothing techniques, the probability that you end up giving to those kind of unknown words will be very, very small. And consequently, the overall probability could be very small in predicting some tag sequences which involve some unknown words and all. So instead of directly considering words, if there is a way to consider some features associated with the words, right? And like, for example, capitalization or the morphological structure of the words, whether it is ending in ing, whether it is ending in ed, for example, in the case of verb and all. And it will be, if we can consider these kind of features in our model, and try to predict this tag sequence, taking into account all these different various features as well as the words also, and as well as some sentences. The overall, for example, the whole globally, there could be some features we can extract from the sentence, and in predicting the tag sequence, can we make use of those features? Okay. So how to make use of all these different features, which is locally present in individual words as well as globally present across the sentences, in predicting our tag sequence. So that is not possible with a hidden Markov model, and it will be useful in performing prediction of tag sequence, and it will be helpful in generalizing to sentences and words which are not seen at the training time. Okay? And this is where a discriminative modeling could be useful. Okay. And for the case of test classification, we may use something like a logistic regression. And in the case of sequence labeling, we use something called conditional random field. And the conditional random field can be seen as a kind of a generalization of logistic regression models for sequence labeling problems. So we will see exactly how it is going to model. But the conditional random fields, taken generally when you use conditional random field for uh, problems in NLP, you construct, or it provides a way to consider and construct a lot of features, additional features, which can be helpful for part of speech tagging. Okay, and in practice also, they seems to give a much better generalization performance than hidden Markov models for problems involving natural language processing.
Sir, are we saying that hidden Markov model would work better when we are using the words which are actually part of the training model, but in the terms of generalization, conditional random field is a better performing model?
Right, yes.
Okay.
Yeah. So So as I said before, CRF is a discriminative model. It's a discriminative model. And in a discriminative model, we try to directly model this probability of y given x without considering this decomposition into s given y into p of y. So we never try to model x. Okay. So that's how it is different from a generative model. In a generative model, we try to model x also in addition to modeling y, right? So this is representing the joint distribution x comma y, right? So we try to model this x and y in a generative model. But in the case of a discriminative model, we don't care about how the x's are distributed. We only try to model the distribution of our y given some x, assuming some x is given to us. And the way specifically the the conditional model condition the conditional random fields model says p of y given x is by considering so extracting out several features from these x and y pair, okay? And then considering the probability using a softmax function, right? So assume fkxy are the features that you have extracted. We'll see an example of what are the features uh, from a input output pair x and y. Now, then you can simply think of this as a logistic regression. So this is nothing but this is exactly how a logistic regression model works, right? So the logistic regression model, you consider some linear combination over features something like WK transpose X, right? And then no, you consider some normalization over all possible labels. Here, all possible labels is Y, and that will give you a probability of Y given X, right? So what is happening here is nothing but the softmax function that you have used in a case of a logistic regression. But now if you look at the features, you are extracting some features out of your input-output pair X and Y, each of which is a sequence. So now if you look at this, again, there is a issue. The issue is this. So if you look at this denominator term, the denominator term involves a summation over all y dash. And your y dash is a sequence of labels. And as we have seen before, this summation requires you, exponential time, like you need to perform summation over a very large number of sequences, which makes this computation of the probability intractable. To make it tractable, conditional random field uses some particular tricks. Okay, and now one of the ways you can make this tractable is by considering some features of this form. Okay? So when it considers the features, it considers some features of this form, where it considers features over consecutive pair of labels yi minus 1 yi and the input x. Okay, so the features, it consists of forms this kind of a nature, where you forms features out based upon all these consecutive pairs of labels which are present, or consecutive pairs of labels that you are considering. And this way of considering features allows it to perform this summation in a computationally efficient manner. I think I have a slide which shows that. Yeah, I have a slide which shows that. But this is the way the conditional random field considers features. So it considers features of this nature, where it forms different features by considering consecutive label pairs and the input.
But
And
but how
yeah.
it handles those unknown values or those features? How it generates features for those unknown tokens?
Because the way it forms these features, which involves xt, is, for example, in this example that is given here, you have something like xt is some particular word and yt is known. But you can form features by saying that, okay, the xt is capitalized and yt is known. So your feature can be something like that also. It need not be exactly xt is equal to some particular word brown and yt is equal to noun, but it could be like, your feature. Okay, your feature is something like this. Okay, you can have a feature like you 110 xt yt is going to be equal to 1 if xt is capitalized
Okay.
and yt is noun and 0 otherwise. Okay. So you can construct these kind of features also in a conditional random field set. Okay, and that allows it to generalize to unknown words or unseen words.
Sir,
right?
these
So
features, these features are just calculated from this X and Y pair. My question is like in the previous slide, we had summation over labels, and that's why we told that the computation becomes very, yeah. But the feature, how this feature is going to help this computation here? Because summation will
yeah,
still be there, right?
yeah, the summation will be still be there, but we will see that summation also can be now brought inside. Okay, the this we can bring these summation over these different components inside, and we can do it more efficiently, like the way we have seen in the case of hidden Markov model. And to do that, it maintain a features of this nature. Okay, the features it considers no, it will be having a form like this. No, b of yt minus 1 yt. It considers only pairs of features. Okay, features extracted out of pairs of labels, and something of this nature, xt yt. Okay, and the features which it constructs out of xt yt could be something like this. Okay, where no one feature could be like if xt is brown and yt is noun, it will be 1. As I said, another feature could be like if xt is capitalized and yt is noun, it will be 1. And you know, you can construct several features in this way, and the features it constructs based upon these label pairs could be like this. If yt minus 1 is noun and yt is verb, it will take a value of 1, and otherwise it is going to be 0. Right? So yeah, so the features it forms these are the examples of some of the features, and once you form all these features out of all your pairs of consecutive labels that you are considering, then you can consider this kind of a model similar to logistic regression, where you learn these weight coefficients, and you can, once you have these weight coefficients, you can make predictions by considering these softmax kind of a probability. But in any case, okay, in computing the softmax and during the training time also, you will have to deal with this summation over all y. Okay, and now let's see how we can deal with that. Here is one more example that you have. For example, this is this could be some set of features one can consider as part of conditional random field, like xi contains a particular prefix, xi contains a particular suffix. So xi is short word shape. I don't know what it is, but no, you can based upon, or maybe like the length of the word, etc., can be a feature. No, you can consider several such kind of features and construct a condition random field based upon all these features. Yeah. Yeah. So basically, uh, when you want to perform inference, again, you may want to perform this argmax operation over p of y given x. So see, as far as the inference is concerned, so in inference time, you can possibly ignore that denominator that you have, and you may need to perform this argmax over this numerator term that you have. So the numerator term that you have, we can write it in a form like this. The key are all the different. Okay. You have this summation over I equal to 1 to n, which is over this sequence. You are assuming this length of the sequence to be something like n here. Yeah. So if you look at this nature of this this component that you have here, see, because of the way it has structured, like now the features are formed only out of consecutive pairs of labels. When you want to do this argmax operation, you can use a similar kind of an idea that we have discussed previously, where you can bring in these max operation inside these summation terms, and you can find out this in a very efficient manner. No, so the same ideas that we have discussed holds here, and we can do this inference in a efficient manner. And in the case of learning of the parameters, while learning of the parameters, you need to maximize this quantity, right? In the case, as in the case of a logistic regression, you learn the parameters by maximizing this quantity. And of course, it involves this summation term. And this summation term also can be brought inside by considering this 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 particular representation of the features that you have, and that again can be computed in an efficient manner, like we had in discussed the case of HML. Okay.
So one doubt here. So is the CRF is basically if we have lots of kinds of stop words in our data, in our sentence whose frequency is much higher, those tokens, so it will impact the CRF results, right?
If you have a lot of stop words,
those tokens which are basically less in importance, but have the frequency of them is very high, so that will affect the probability distribution, right? And probability calculations, and that will affect our the calculation that we are going to do in CRF.
I'm wondering how that is going to affect. Why do you say that would have some?
You are getting a feature of yt minus 1 yt and x and t, right? So and if basically and there are weights associated with each of those word tokens, wi, so will not occurrence of a certain tokens, a very high number will give them much more weights.
Even if it gets a lot of weights, say, I don't see. I don't understand how it can affect the. eventually we have to perform sequence labeling where we want to assign part of speech tag to each of these words. And now if your label sequence, I still don't understand what effect you're trying to say. What effect? How exactly is it going to affect your sequence of labels that you want to assign? Do you see that if there is a
I mean to
if there
say
are
that
more stoppers, it will end up giving some wrong assignment of labels to the
uh,
sequence.
I just want to say that if we employ some other algorithms like LSTMs and we have a word embedding for each of those word tokens, so that basically takes into account the meaning of those words, right? But here we are taking into account the probabilistic values for the word tokens. So so here let's say if one sentence is there in which the is occurring adjacent to a target in the word which if we are really very interested, like near in the slide that you had shown earlier. So if the is occurring adjacent to it and after it also multiple number of times, or or so will that affect the occurrence of it will affect at the test time uh, in getting its label across one particular category. That I was interested in knowing that, because in naive base we had discussed that probabilistic interpretation get affected by the count uh, uh, of those values. um, is it
See, in
clear?
an ABS classifier, okay, if you can see, for example, if for one class, if the is appearing very large number of times, and for the other class, the is appearing very less number of times, then it will be having some effect. That's what you are saying, right?
Yeah. But here, will it affect the adjacent keywords, adjacent words value? Because we are doing the sequence labeling here with respect to the previous words.
Yeah, I don't have any idea of what you end up learning as a weight values in this situation when you have this, when you have some kind of a discriminative model. I don't know like what is happening and what you end up learning as a weight coefficients. See, even in any case, okay, so here we are not trying to predict a single label for a whole sentence. I mean, if you're trying to predict a single label for a whole sentence, maybe like the appearance of the or something large number of times might have some effect. But you try to predict for each word some label, right? And like if okay, like no, so see, for example, what you are saying is that okay, uh, uh, if there is a word and uh,
So I think, sir, this is a
like that
kind of
word is, yeah, I don't know, like what is it?
kind of class imbalance problem, right? So, suppose a extreme condition where only 2 3 words are there and they occurs repeatedly many times, so that probability will be very high. Other like if in the test time we see that is kind of word, and that's probability is very less, kind of zero, and it never saw those things in the extreme situation, so it will get affected, so model will not perform better there. So the idea will be that if we see such kind of repeated word, and when we plot the distribution of the data with this previous and next, and we see that there is a imbalance, some repeated word are coming many times, we might want to include more corpus in the data, so that it's like imbalance is not there. So mostly all kind of problems get affected if there are some more repeated data, and that we can see in the field when the model is deployed, right? So the extreme condition we can see that, suppose we have a corpus where there is a word like there is, and this there is repeated so many times that like 90% of the data is only there is, and thereafter you got some other words. In that case, if we now use this model on that kind of data, it will not perform good when we do the inferencing.
What do you mean by it is not performing good?
It won't be able to provide your label correctly, the POS level, because those POS level it might not have seen. It didn't learn the weight for that, because it occurred very less frequent, or it never occurred. Like if you take to the extreme, less frequent might go to never, right? And frequent go to like it just appeared many times, or that only thing is there in the data in the extreme situation. Then we say that in the data only those kind of levels are occurring always. So because model will learn this, weights will learn that thing, and it never seen those data other parts of speech, uh, then it won't be able to predict those parts of speech. And if the probability of some parts of speech coming together is a lot, then it will learn, or it will try to search those kind of things when in the inferencing time. It's just kind of intuition, I'm not sure.
Yes, that is true. That could happen in this case also. The case of conditional random fields also. So we no, so no, that case could have. We said that that will happen in the case of hidden Markov model, but the same situation it could happen in the case of a conditional random field also. Just that no, it is less prone to those situations. Is less prone to situations, to tackle unseen words. Probably not unseen pair of labels. If some label pairs are not seen, um, I maybe it could happen that no, it is not going to predict that at the time of testing also, unless I don't know if it can if one can construct some features which can help it to generalize to those unseen label pairs from some seen label pairs. But this could be conditional defense could be more effective for dealing with uh, unseen or unknown words, because you can construct some features which can help on to generalize to those unseen words by considering some structure of these words. Yeah. So yeah, maybe that is true in the case of conditional random field also. I can say that no, HMM can be much more prone to uh, unknown words as well as unseen sequence of tags, while conditional random fields are less prone to unseen words, but it can still be prone to unseen sequence of tags. I mean, it may not predict well for some unseen sequence of tracks, which it is not seen on the training data set.
And sir, why is this name conditional random field? Is there anything to do with the algorithm here with this name?
Okay. So it has nothing to do. It's a graphical model. So in graphical models, there are majorly two type of approaches. One is based upon directed graph, and the other is known as other is based upon the undirected graphical model. So these directed graphical models are often known as the Bayesian networks, and the undirected graphical models are generally known as random fields, and that majorly comes from the graphical model literature.
Oh, okay, sir. Thank you.
Yeah. So yeah, we will stop here for today, and we'll discuss this with maybe some other time. And
Sir, for the slide, will it be available over the Teams? The slides that you have shared
yeah,
in,
I will upload in the Teams classroom. Yeah,
and the recordings will be also in Teams, right?
we are recording, right?
Yeah.
Yes, it will be in Teams.
Yeah. Thank you, sir. Sir, one more question. For this slide and everything, which book you are referring?
So you can follow very nice book on NLPs, Jurowski and Martin. I think it is, what's the name of title? I will tell you 1 minute.
And sir, while sharing that,
It's called Speech and Language Processing.
Yes.
By Jurowski and Martin. So you can find out the I mean, they have made it publicly available, lots of different chapters in their book, so you can easily find out. Maybe you can just write it down.
Right, sir.
So, sir, this is Zerowski and Martin, right?
Yeah.
So just for like asking, what are the topics that we are planning to cover in the next day?
I think the next few classes, I mean, I will be continuing with the sequence labeling models, sequence labeling approaches based upon deep learning models, etc. And Professor Maunendra would be covering these representations of documents and words, maybe like unigram, bigram, and then these distributed representations based upon word to word, etc. So,
Sir,
these are the immediate.
is there any plan, sir, that which faculty will cover which part?
Yeah, so these are the topics, and all these parsing Then co-reference resolution, discourse analysis, all these Professor Manindra will be covering. And a representation, yeah, maybe some of them I will also cover. And so some of the topics in deep learning Manindra also covers. So we haven't exactly divided it, but more or less these are the different topics which will be covered in the course.
Okay, sir. So next class you will be taking, or Professor Monindra will be taking?
Mostly Professor Manindra will be teaching.
Okay, sir. Got it, sir. Yeah. So please upload the PPT so that I can refer to the PPT.
Sure, sure.
And sir, can you please save those annotation or writing so that we can even refer to those things? So while saving the PPT, somehow if you can save those writings.
Sure, sure. I can share this thing. Yes.
Sir, can you also share about quizzes and assignments?
You can check with Professor Manindra. So I think, see, following what we did last time, there will be few quizzes, and there will be maybe we can you can check with Professor Manindra in the next class.
Sure, sir. Sure. Thank you.
Okay, sir. Thank you.
Professor, one small request. Can this class timing be scheduled to morning time, as most of the people are taking this course? And
most of the people are not taking converse optimization, is it?
Yeah, that's it.
How many of you are taking converse optimization?
I'm taking converse optimization.
Anybody else?
From the MDS 2023, nobody is taking.
But Savastri is MDS 2023, right?
Yes, is not taking.
I haven't taken convex optimization also.
Sorry?
Okay.
I haven't taken convex optimization, sir. Nobody is from
Okay.
taken convex optimization.
Okay, sure. Yeah, let's see. Anyway, now we will get a better idea. Yeah, maybe more. Yeah, we will see that. So can you get a rough idea how many are taking? How do I get know? Like maybe you can message here or do something. How many of you are taking converse optimization?
And when is the class, by the way, for this converse optimization?
It
At
also
what time?
varies. I think it is also varying. Can you tell me how, if you're like, can you get a rough idea how many are taking converse optimization? Maybe like you can just message here. Or...
No one from MDS 23 for sure.
Yeah, sir.
Okay.
From MDS 22, I guess 2 or 3 people will be here.
MDS 22, 2 or 3 people is taking converse optimization or
Yeah.
taking NLP?
No, both.
Okay, sure.
Even sir, if one student is also taking the class, it's going to be a problem for them, right? They won't be able to attend if it overlaps.
Just the request for rescheduling the timing part, Abhishek.
Okay.
By the way, when is the converse optimization timing? Do you have any idea?
It keeps varying, I guess. When is it? Do you have some idea?
Yeah, we have to schedule in that Excel 2024 Excel for converse.
Sometimes it is in the evening and sometimes it is in the morning, right?
Yeah.
But you're all only 22 is taking deep learning, right?
23.
We are only offering
23.
deep learning and NLP, sir.
Yeah.
Okay.